you define T of F0 is just OL cross, and then T of F, how should I define this? So T of FR is the set of all X in T of F0 such that the valuation of X minus 1 is greater than or equal to R. Okay, here X is in OL cross. I've identified T of F0 with OL cross, and then T of FR is given by this. And now in the where do the jumps in the jumps in the filtration occur? So for note that okay, so this is the I hope I said this last time. So this is the valuation which is normalized so that the value group of F cross is Z, right? So then this will happen, and this extends uniquely to a valuation on L cross, and this will happen exactly. So the jumps they occur at 1 over E times Z, where E is the ramification index of L over F. Okay. So for the torus, the defining the filtration was easy, but when we try to do the same thing for root subgroups, things do get difficult. Already note that in the case of SU3, okay. So let me let me write this down. So sorry. So we also have to define a filtration on the root subgroups, but already there are but what are the root subgroups that we have to consider? Note that we have two. So just with the setup we are in, we already have two root systems floating here. So you have the absolute root systems, which is the set of roots of T in G, and then you also have the relative root system, which is the set of roots of S in G. Okay, so we have two root systems here, in the picture. What is it? So the absolute root system phi of GT, and the relative root system phi of GS. So when you look at the absolute root system, you're already going to base, you look at the root system after you base change the group to an algebraically closed, to a separable closure. So this is just the root system for SL3. Okay, but then you also have a relative root system, and for SU3, this actually turns out to be a non-reduced root system. So this is a non-reduced system. So it is a case where a root and its multiple 2A and 2A are both roots here. So I won't be able to sort of explain everything in this, but I'll just say a few things. Okay, so as I said, so what is X lower star T? So when I look at the X lower star T, I'm looking at forms from GM to T, but again over K sep. So this is just whatever you see for SL3. So if I with the diagonal coordinates, I get that this is the set of all X, Y, Z in Z cube, such that X plus Y plus Z is 0. And similarly, X upper star T is Z cube mod Z, where Z sits inside Z cube diagonally. These are just the character and co-character lattices for T, but we're just doing it inside SL3. Okay, diagonally embedding. Okay, and how does so you do have that? So also X lower star S sits inside X lower star T. you take a character from GM to S, and then you have an embedding from S to T, so you get a character from GM to T. So you do get an embedding from X lower star S to X lower star T, and also a surjection from X upper star T to X upper star S. So under these, what is no? I'll just say here, no, X low S, the torus S as an algebraic group was just isomorphic to GM. So X lower star S and X upper star S are just both isomorphic to just Z. Okay, so I just have to identify how, I just have to tell you how Z sits inside X lower star T and how this surjects onto Z. Okay, so what is this map? I take an element A and I send it to A0 minus A, and in this map, in this quotient, I take X, Y, Z, and I send it to X minus Z. Okay, so this is how the character and co-character lattices of S are related to the character and co-character lattices of T. Okay, now you have the absolute root system. I'll write down what it is. So this is the root system for SL3. I have made a choice of this diagonal torus and a Borel, which is the upper triangular matrices in SL3. So relative to that, I'll get a system of positive roots. So it has 3 positive roots, which we will denoted as A tilde prime and B, and where B is A tilde plus A tilde prime. And what is it? I mean, with respect to the standard choices, this is just A tilde is 1. I mean, after I identify X upper star T and X lower star T with these, A tilde is just 1 minus 1 0, and A tilde prime is 0 1 minus 1, and B tilde, oh sorry, B, I've just called it B, it is 1 0 minus 1. Okay, so what are these? The absolute root system is the set of roots of T in G, which is basically the weights for the action of T on the Lie algebra of G over L, which is now just SL3. Similarly, you have a relative root system. Okay, so these are the weights of the action of S on the Lie algebra of G. So this leads to as I said, this leads to a non-reduced root system. With positive relative roots. I'll denote it as A and 2A. These are roots, so they are contained in X upper star S. And what is the map? And the map from under the map from X upper star T to X upper star S. A tilde restricts to A. A tilde prime also restricts to the root A, and B restricts to the root. B is A tilde plus A tilde prime, so it restricts to the root 2A. Okay, so this is an instance of a non-reduced root system where A and 2A are both roots. Now, what about the root subgroups? What about the root subgroups? So how would you figure out what the root subgroups are? I mean, okay, so that is, I mean, I've written down already what the relative roots are. So these are these are the weights for the action of S on the Lie algebra of G. So it is, so how do you calculate the root subgroup? So I'll take the upper triangle, so take the unipotent of the Borel subgroup in SL3, and identify and consider those matrices G such that G bar is G transpose inverse G. Okay, so these are the matrices in SU3F, right? The matrices in SL3L which satisfy this condition. So now I want to figure out what the root subgroups relative to these roots A and 2A are. So for that, I will look at the unipotent radical of the Borel in SL3 and look for matrices that satisfy this condition. Now, you know, it is not hard to show this. This is an elementary calculation. So this is the set of all I mean, I have looked at the upper triangular matrices. So 1, 1, 1, U, U bar, and V, where U, V are both elements of L, and it satisfies the condition that yeah, U bar is V plus V bar. Okay, so this is UA of F, and inside that you have the root subgroup U2A, which is the set of all 1, 0, V, 0, 1, 0, 0, 0, 1, where now V is in L and V plus V bar is 0. Note that we are basically U2A of F is basically all the elements of, consists of all the elements of L whose trace is 0. Okay, so let me introduce this. Let L0 be the set of all V in L such that the trace of V is 0. V bar, remember, it is the Galois conjugate of V. So this is the set of all. So this, note that this is a vector space over K. Sorry, vector space over F. But in general, it's not a field by itself or anything. Okay, so U2A of F is L0, so it has the structure of a vector space over F. Now, and U2A of F is isomorphic to L0 as groups. Okay, so now define XA of UV. This is the analog of the XA that I had defined from GA to G for SL2. I'm defining the same pinning here for SU3. Okay, define XA of UV to be the set of all, to be this matrix 1, U bar, V, 0, 1, 0, 0, 1. And similarly, and X minus A of UV, I mean, it's the lower triangular one. So U bar, V. Okay. And okay, I mean, again, if you know the theory for SU3 already, these things might make sense to you, but otherwise, I'm sorry. But anyway, note that the root subgroup UA for SL2, all the root subgroups were just isomorphic to GA as algebraic groups, but that's not what happens for SU3. The root subgroup UA is not isomorphic to GA as algebraic groups, okay? And even, in fact, even U2A is not, but this is what we have. Now, note U2A of F is isomorphic to L0 as groups. So now I have told you what the root subgroups look like. What do I need to do next? I need to define filtrations on these root subgroups. The field L and the field F carry natural filtrations given by powers of the maximal ideal. But the question is, how do you use that to define a filtration on UA and U2A so that it has some reasonable property? So let me start with, so on L, we have a natural filtration. Right, PL to the power minus 2, it contains PL to the power minus 1. Okay, OL contains PL and so on. And at least for U2A, one possibility is what? So on so we want to use this. To define filtrations on the on UA and U2A. Okay, this is what we want to do. So, at least for U2A, we could take this filtration on L and intersect it with L0. Now, what you already know, we know the value group of L cross is 1 over Ez. But if we want to, so to understand where the filtrations of U2A C's jumps, we need to understand what this is. L0, now L upper 0. We need to understand the value group of L upper 0 minus 0. Okay. Now this is I will give you a reference for this, but this is I'll state this as a lemma maybe. Lemma. And a reference for this is lemma 2.8.1 of Kaleta Prasad. Okay. So if L over F is unramified, then this value group, the value group of L0 minus 0 is just Z. But if L over F is ramified, then the value group of L0 minus 0 is given by Z plus 1/2 plus mu. I will not formally introduce what the mu is, but where I'll tell you what it is, where, I mean, after some work, you can show that where mu is minus S over 2, here S is uniquely defined by the property that the Galois group of L over F, S is not equal to 1, but the Galois group of L over F, S plus 1 is 1. Okay, or let me just say this is S plus. Okay. Okay, I have to introduce what these are. I mean, I'm not going to define them again. So this is this group is the lower numbering filtration. No, lower numbering filtration on the Galois group of L over F. Okay, so you can this is defined and explained in Sayre's book on local fields, chapter 4. So the Galois group of L over F is a group of order 2. There is a unique point in the filtration, in the lower numbering filtration of the Galois group, where it goes from being non-trivial to being trivial. It is that jump S that appears in the value group of L0 minus 0. Okay, so unlike the case of SL2 or even what one would hope for, that this will just depend on somehow the ramification index of L over F, that's not the case. It actually depends on some finer information which comes from the lower numbering filtration of the Galois group of L over F. So so when you define the filtration, when L over F is unramified, it is just what you would do naturally. And note also here that if the extension is actually tamely ramified, then this mu is 0. But when the extension is wildly ramified, depending on how wildly ramified it is, this S can that is what this S will pick up. So when L over F is wildly ramified, this is one has to deal with this element mu. Okay, so but for our purposes, I don't want to go. I just wanted to point out that there is a subtlety here when L over F is ramified. So for me, for us, for today, I will just assume that my extension is unramified. We will assume that L over F is unramified. Okay. Now, then you once you assume this, you just okay. Now just define. which means that the value group of L0 takes up is just Z. The value, I mean, when L over F is unramified, the ramification index is of course 1. So the value group of L cross, the value group of F cross, and the value group of L0 are all Z in this case. Okay, so we are in a very, very simple situation. And now define U2A of F R to be the set of all XA of 0V, where V belongs to L0, V belongs to L0, and the valuation of V is greater than or equal to R. Okay, this is what this is the obvious filtration, obvious definition one would give, and that's what we give here. And now consider, I've done it for U2A now, but note U2A of F is contained in UA of F, I mean, of course, by definition. And the quotient UA of F mod U2A of F is isomorphic to L as groups. And how is this happening? So I'll take an XA of UB in this quotient and just send it to you. Okay, so this is actually an isomorphism of groups. And I have this. Now I want to define a filtration on UA of F as well, right? So consider UA of F, which is the set of all 1 UV 0 1 U bar 0 0 1. Again, I have UV in L. U bar is V plus V bar. This is my UA. So what would you do? One obvious thing one could do is you could define a two variable filtration, right? UA of F R1 comma R2. So one could consider UA of F R1 comma R2, which is the set of all XA of UV, where the valuation of U is greater than or equal to R1 and the valuation of V is greater than or equal to R2. Okay. Now, but what is I just want to sort of go to the actual definition that we give for the filtration. So what do you observe? So note, the valuation of V is greater than or equal to R2 implies that the valuation of V plus V bar, which is greater than or equal to the minimum of the valuation of V and the valuation of V bar, but both of them are R2, so this is still greater than or equal to R2, which implies that 2 times the valuation of U is greater than or equal to R2, which implies that the valuation of U is greater than or equal to R2 over 2. Okay, so this condition is sort of forced by this relation that U bar is equal to V plus V bar, that the valuation of whatever is the valuation of V, the valuation of U is greater than or equal to half of that. Okay, so then consider the simplification. Where I just define UA of F R is the set of all XA of UV, where UV and L. I've already written it. Okay, sorry. U bar is V plus V bar, and then the valuation of U is greater than or equal to R. The valuation of V is now greater than or equal to 2R. Okay. But what does this mean? But this is again equal to the set of all XA of UV, such that the valuation of V is greater than or equal to 2R. Because if the valuation of V is greater than or equal to 2R, then the same calculation that I did above forces the valuation of U to be greater than or equal to R. So this condition is automatic. Okay, so this is just what I have, and this is how we define the filtration of UA of F. Okay. Now, where are the jumps in this filtration? So summary. The jumps in the filtration for U2A of F R is when at R in Z, and for UA of F R is at R in 1/2 Z. Okay, because valuation of V is greater than or equal to 2R. So it happens at 1/2 Z. Now that we have defined the filtrations in the both for the torus and for the root subgroups for SU3, I can now define my apartment. What do I want to do at every point? Okay, so let me write down what my apartment is. The standard apartment for SU3. For SU3. Okay, so let A. As I said, I think I mentioned this last time a few times. So the apartments in the building are indexed by the maximal split tori in SU3. In this case, we had a maximal split torus, and it's the relative roots. It's that relative root system on which we have defined these filtrations. Okay, so let A be X lower star S tensor over Z with R, which is just R again, because as X lower star S is just isomorphic to Z. We saw this earlier. So this is just a copy of R. And again, at every point on R, we want to define this subgroup Px. And then somehow the places where these Px, okay, so let me write, sorry, I can't, let me write this down. Okay, so I have this, and for X in A, we have defined, we have already defined UA of F A V and UA of U2A of F 2AV. What is this pairing? So V is an element of X lower star S tensor R. So this is just the R linear pairing extending the usual pairing between X lower star S and X upper star S. Okay, sorry, X upper star S. So the elements A and 2A are roots. They live in X upper star S, and then I have yeah, I have. Okay, I don't know if that's okay, but anyway, I'll not get into that. Okay, but V is an element of X lower star S, and then I just consider this pairing. This is, I'll put this in quotes because this is okay. Now let us say V is special if at least one of the filtrations jumps at V. One of the filtrations UA of F or U2A of F jumps at V. By that I mean that is at least one of the inequalities UA of F, the pairing between A and B, is not equal to UA of F, the pairing between A and B plus. Okay, I have to introduce what this is. I'll do that in a minute. Or UA of U2A of F 2AV is not equal to U2A of F 2AV plus at least one of these inequalities holds, where UA of F AB plus is the union of all R greater than AB UA of F R. Okay, so this is the definition of UA of F. This is the definition of this subgroup UA R plus. Okay, it's the union over all S greater than R of UA of Fs. So in this case, this is what it is. And so why are we defining this? I'll just explain. I'll just briefly motivate it. Okay, the first one holds. So let me label this inequality as 1 and this as 2. The first one, that is 1, holds. When does 1 hold? When if and only if this AB belongs to 1/2 Z, and 2 holds if and only if 2AV, the pairing between 2A and V, belongs to Z. So of course, one holds if and only if two holds. So you don't need to have two separate conditions here. So what does this mean? So this means that this means that V is special if and only if AV, the pairing between A and V, belongs to 1/2 Z. Now, why I'll explain why I have defined this in a minute. So for V and A, let PV be the subgroup exactly like I defined last time. So it is T of F 0 together with UB of F. But here I have the pairing between minus B and V, where B belong. Sorry. Where B belongs to A minus A, 2A and minus 2A. Okay. This is exactly how we had defined the PX last time. But what is happening, and then I can also look at PV plus, right? I define it exactly the way I defined it earlier. So this is T of F 0 plus and UB of F, the pairing between minus BV plus, where again B belongs to A minus A, 2A and minus 2A. Okay, so what we want to do is, so now note, if V is not special, what does this mean? If V is not special, then UB of F, the pairing between B and V, equals UB of F, the pairing between BV plus, and the same thing for both A and 2A, right? This is what holds for both for all B. But what does this mean? This means that if I look at the quotient PV mod PV plus, this is just the, I mean, you have to justify this. This is the quotient of T of F 0 mod T of F 0 plus. So this actually turns out to be the kappa F points. I mean, kappa F is the residue field of F, kappa F points of a torus T. Now I'll write it as T underlined. Okay, but on the other hand, if V is special, then this group, then this quotient PV mod PV plus is actually the kappa F points of a certain connected reductive group over kappa F points of a certain connected reductive group defined over kappa F. Okay, so this is the okay, so so what are in the, I mean, I'm running out of time, so I have to sort of start wrapping up. So at least in the case of SU3, the possible quotients that appear are SL2, or I mean, I already saw the torus. SL2 appears as one of these reductive quotients. SU3 can appear, or PGL2 can also appear. Okay, so these are the possible quotients that can appear for this connected reductive group. This is explained in Kalita Prasad, but anyway, so what we want to do, but how do you study? So to study this quotient, we need to understand the quotients UA of F R mod UA of F R plus, and similarly U2A of F R and U2A of F R plus, right? These are the quotients that appear in this quotient. So to understand what this quotient looks like, you have to analyze what these possible quotients are. When V was not special, these quotients were just trivial, but we have assumed that V is not special now. So there is some quotient that appears here. I just want to make one more point related to this. So okay, so but how do you study this quotient? So to study these quotients, you look at consider this exact sequence. So I have one goes to U2A of F. It sits inside UA of F, and it goes to the quotient UA of F mod U2A of F, which I observed is just isomorphic to LS groups. Goes to 1. Yields another exact sequence U2A of F 2R goes to UA of F R goes to UA of F mod U2A of F. Okay, how do I define this? I'll write this down. This 1 goes to 1, where this is UA of F R U2A of F mod U2A of F. Okay, so this is the definition. Okay, so I get this exact sequence, and then I get from here I get which then further yields these exact sequences U2A of F 2R mod U2A of F 2R plus 2UA of F R mod UA of F R plus, and then UA of F. I'll just write this quotient as bar R mod UA of F bar R plus goes to 1. So what happens when this quotient is trivial? So when this quotient is trivial, this implies that you have an isomorphism between the root subgroups U2A of F2R quotiented out by the 2R plus, quotiented out by its quotiented out by U2A of F2R plus, and similarly the one for UA. Now, so what happens is, so when you try to analyze the quotient Px mod Px plus, it's not just the jumps in these two filtrations that are relevant, but you also need to know where the jumps in the filtration of this quotient occur. Okay, so we also need to understand the jumps in the filtration of UA of F R bar mod UA of F bar R plus. Okay, but okay, so I will give you a reference for this. So this is lemma 3.2.5 of Kalita Prasad. So, but once you go through that lemma, and you will be able to justify this claim. In addition to the case where you had the torus, I think these are the only possibilities. And then gives gives a complete description of PV mod PV plus PV mod PV plus for BAV. Okay, and these considerations will lead you to define the affine roots as before. So I mean, as in the case of SL2, the jumps in the filtration of the root subgroups, and consequently for the where this quotient was non-trivial, is what motivated us to define the affine roots there. So it's the same thing here. So you define the affine roots as an affine linear functional, xi from A to R is an affine root. If one, of course, its derivative so I'll write xi as B is a root. So B is basically an element of A to A minus A or minus 2A. It's an element of this set. And xi is B plus R, where R and R. But now what is this R like in the case of SL2? This R is supposed to keep some information about where these quotients are non-trivial. So 2R is a jump for the filtration UB of F if B belongs to 2A and minus 2A and is a jump for the filtration UB of F mod U2B of F if B belongs to A comma minus A. And with this, you can, so this is the definition of the affine root, the collection of affine root. This is the collection of affine roots for SU3. And then the rest of the story is the same. You can define the affine while group as before. This is the normalizer of F mod T of F0. This is how the affine while group is defined. And like last time, you can define an action of the normalizer on the apartment, can define an action of ng of S of F on the apartment on A by, we did it in 2 steps by defining the action of T of F, which was basically by translations in a sort of very precise way by translations, and by defining the action of W, which is ng of S of W0, the finite relative value mod T of F, the full T of F. Okay, so you define the affine while group. Again, it acts on the apartment, it preserves the simplicial structure. And now finally you define the building for SU3. The building is defined exactly as last time. So you take the set, look at the set G of F cross A, and you define the equivalence relation, and define the equivalence relation by saying that Gx is equivalent to Hy if and only if there exists n in the normalizer now of S of F such that n dot x equals y, and G inverse Hn belongs to the parahoric subgroup Px. Okay, so this is the definition of the building of the group SU3. Again, I think I skipped many things. Unlike the SL2 case, I could not explain many steps, but this is explained very carefully in the book of Kalita Prasad, chapter 3. So I would suggest you look at it after if you're interested. I think I'll stop here.
Thank you so much, Radhika, for the wonderful talk. Are there any questions from the participants? Okay, if there is no question, then let us thank the speaker for the nice lecture.
Yeah, thanks. Thanks, Srilakshmi.
Thanks, Radhika.
Bye. Bye.